I think we're recording.
Okay, my magic fingers may have actually worked. Does it look like it's recording?
Yeah.
Okay, so be mindful of the beeps. Okay, today we're going to begin integration. I'm going to start by reviewing the Calc 1 stuff because we take that and we build off this. And I mean all the way back, not how to integrate, but the actual theory behind it, fundamental theorem of calculus kind of stuff. So in Calc 1, what we did was we started with a picture, use different colors here, and we said we want the area under the curve from A to B of y equals f of x, okay? So what we did was we partitioned this. Now understand, a partition is random in this case. And what we did was we said, let's make n rectangles of varying widths, okay? And then when I'm squaring these off, I can choose any place in the interval to square it off. In some cases, I might do it from the middle, some I might do it from the right endpoint, some I might do it from the left endpoint. But again, the partitioning is essentially random in the widths and random in the place where I choose to do the heights. And the interesting thing is, if I am completely random, it's possible that when I add up these areas, it actually could add up to the area of the integral. Whereas if I said, no, let's use all the right endpoints, or let's use the left endpoints, or let's use the midpoints, then it actually can't add up. Now, how do I get the actual area? Well, obviously, we know there's a limit in there somewhere. So if this is x0, and this is x1, and x2, and so on, we know that delta x1 is x1 minus x0. Delta x2 is x2 minus x1, and so on. So delta xi is xi minus xi minus 1. So what we're going to do is take the ith rectangle, this one here, okay? We take the ith rectangle and we said, let's find the area of that guy. Now, technically, if this is xi minus 1 and this is xi, then we call the place where we evaluated it wi, where wi is anywhere in that interval. Wi could be the left endpoint, it could be the right endpoint, or it could be any value in between. It's any real number, and it's a or equals, because it could be either endpoint. What we did was we calculated the height from that value, so we said the area of the ith rectangle, the ith area, in other words, is f of wi times delta xi. Then we can say the overall area can be estimated by the sum from I equal 1 to n of this quantity right here. Now, this is not going to equal the area, but we know it's a reasonable estimator. How do we get the equals? Well, we make the rectangles get smaller. Now this is the part that often throws people, and we sometimes forget this. We did this with arc length already, right? When we take the limit, we're taking the limit as the norm of the partition, okay, as this guy approaches 0 of this sum. Now this feels very theoretical. The norm of the partition, in this case, norm would refer to the largest such width. Norm in this case would be a length unit. It doesn't always have to be a length unit. The norm of the partition is considered the largest width, and if the largest width is going to 0, then all the other ones. Now, in Calc 1, I do this every semester in Calc 1, is I bring my weapon of mass destruction to class. See, I'm trying to join the Evil Genius League, and to do so you have to have two things. You have to have an evil layer, I do, and you have to have a weapon of mass destruction. Mine is the shrink ray. And so what I do is I find the biggest person in class, might be today, Tommy, and then eventually, and I take each person and I shrink them to 1 point. Eventually, everybody here at some point is going to be the biggest person in class, aren't they? Because everyone before you got shrunk. So I'm shrinking the biggest person in class down to a single point. Don't worry, later, if I just pour water on you, you come back. But it's kind of a traumatic experience for Calc 1 students to be shrunk to a point. But I have to make a point. So I'm actually describing this to the T. That's what we're doing. We're taking every width and shrinking it down to 0. So if the biggest width is going to 0, then now there's a new biggest width, and it's going to 0, and then there's a new biggest width. In other words, I'm taking each width and I'm subdividing it literally infinitely many times. If I just said, take a delta x and have it go to 0, then all the other ones would remain, wouldn't they? They wouldn't be changing. I have to have every one of them go to 0, but we only have one independent variable. I can't make them all go to 0 simultaneously. So the language is, the largest one is approaching 0, so there's always a new largest one. So that's approaching 0, and then the next new largest one. So as I go around with my shrink ray and shrink the biggest person down to a single point, eventually all persons were shrunk to a single point. All rectangles eventually went to 0. This is called the Riemann sum. You never calculated this. My God, that would be a nightmare to actually calculate. No, this is equal to the definite integral. This is where the definite integral comes from. It is equal to this. Then we learned how to, we already knew how to integrate at this point in Calc 1. We learned where the limits of integration come in. That's what the fundamental theorem of calculus does. It shows us how to actually do the calculation. You guys all know what to do. You find the antiderivative of f of x, you evaluate it at the endpoints. Piece of cake. But it was the development here. Okay? That's Calc 1. So now, what if? Let me go back to my picture now. Everything's the same. But what if I said, you know what? Within each of these rectangles, I have n rectangles. What if I took each rectangle and subdivided it this way? M times. Each one of them exactly m times. Then let's take that one right there. Remember, width-wise, it was delta x's. But what about height-wise? It'd be delta y's, wouldn't they? So this is the ith delta x. Let's say that right here, this is the jth delta y. I and j have nothing to do with each other. So I went over, 27 rectangles this way and up 35 rectangles this way if you choose. So I have this piece right here. Well, if I take the delta x and I multiply it by the delta y, that will give me a new term. We'll call it delta aij, which would simply equal delta y. Well, I'll write it in order, sorry. We'll call it delta xi times delta yj. If I subdivide each of my original delta x's m times into delta y's, now if I said, what's the area of this whole thing? We'll just add up all these rectangles, add up all of these, and so on. It does not matter what the functional height is anymore. Why? Because if I said, take the sum, okay, what do these look like? Well, the first one down here would be delta A I1, delta A I2, delta A I3. Why? Because the x, I'm on the ith x, and then I go 1 through m. Does everybody see that? On the y's. So let me write it a different way. It might make it easier to see. So if I said delta xi is actually equal to, it's actually equal to delta A I1 plus delta A I2 all the way delta A IM, which is the same as saying this is delta xi times delta y1 plus delta xi times delta y2 all the way to delta xi times delta ym. And if I factor out the delta xi, then what am I doing? These are y's, sorry. Well, that is f of xi, or technically f of wi, isn't it? That is the height of the rectangle. If I add up all these guys, I get the height of the rectangle. That's why I don't really need to use the f anymore, because that's what these guys add up to. So would it be correct to say now my area can be estimated by add up all these little rectangles? Yeah, but how do I say that? Well, let's see. Let's go back to here. What does this say right here? Excuse me. This says inside there, that says the sum from j equal 1 to m of the delta yj's times delta xi. I have it right here, don't I? From j equal 1 to m, because the last one's m. So this would be delta y1 plus delta y2 plus delta y3, all the way to delta ym times xi. That's what this quantity right here is. Okay? So if I do that, all right, now, let me erase this so I can fit everything in here. Then I can say that the area, which before was just the sum of the delta x's times the specific f functions, I can actually do it this way. I can say it's, estimated by j equal 1 to m of delta yj. Now I want to add up, I want to start with the first rectangle. So I want add up all the delta y's times delta x1. Now add up all the delta y's times delta x2, and so on, and so on, and so on. It's the sum of the sum. Now this is overcomplicating things. Well, I'm trying to figure out a new way to describe the exact same areas we just did, but by independently adding up x's and y's. So with that, if I now take the limit as the norm of the partition goes to 0 of this, the sum of the sum, you notice the indices have to be different. And you don't need to put the parentheses, but technically, right, because the j only goes here. And then this would be the actual area under the curve. How would I write that as an integral?
Double integral?
Yeah. It'd be the integral of the integral. But before I had an integrand, I had an f of x. Now I don't have an integrand. Because when I add up all the delta y's, that is f of x. Right? F of x came from these guys. So technically I'm going to write it as 1 dy dx. Whoa. Now, this is where it gets kind of crazy. What are the y limits? Well, y in my picture are ranging from 0 to f of x, aren't they? And x was ranging from a to b. And let's see what this would look like. Because evaluating a double integral is a lot like doing partial derivatives. I only do one variable at a time. I want you to think of it like this. This is on the inside. In a sense, this is the integrand of my dx integral. Well, what would this be? Well, just all by itself. Wouldn't this just be y evaluated from 0 to f of x? Isn't that what that would be? Inside this, which would then be what? F of x minus 0. Oh, now we're back to our original integral, which would have been way easier to just start with our original integral. You do not do a double integral to find an area in the xy plane. You do a single integral. We already know that. But I just showed you that if we did it as a double integral, it's consistent. So why would I ever do a double integral? All right. I would like to find the area of the floor. Okay? So, you know, it's a simple geometric region. What if I said instead, you know what, we're standing on something that it's not, I don't want you to think of this as two-dimensional, I want you to think of it as three-dimensional. We're standing on 1 by 1 by 1 cubes. So if I said, what is the volume of the thing we're standing on? Wouldn't you say it's the area of the floor times the height of 1? If they're all 1 by 1 by 1 cubes? So now you could give me a volume because I just gave you a third dimension, but my third dimension was a 1. All right? See this thing we're looking at? It's actually going to be three-dimensional. I'm actually going to have it come out 1 unit this way. It's a three-dimensional shape where the height is a uniform 1 unit. So how would I find the volume? You say, well, take the area, and then multiply it by 1. So if I'm looking at this integral, I could also think of this as a volume where the area in the xy plane is that, but now it has a height of 1. So why would I do such a crazy thing? Because now what if I gave you a height that wasn't 1? Oh, what if I said, okay, the base is whatever the xy plane, but now I give you a surface on top. Then that becomes the double integral with an integrand. Now, there's some generic language that we always use, and it's kind of confusing at first. We put Rxy, that means the region in the xy plane. And then over here we put dA. We are purposely ambiguous. This integral we did as dy dx, but could we have maybe done it dx dy? Yes, I'm going to show you that. You can do it either way. So what the dA says is it's either dy dx or dx dy. You haven't decided yet. By the way, is this still recording? Okay, good.
Yeah, it hasn't beeped yet.
We haven't gotten the beep yet. You have the choice of which way to go. You haven't selected it yet. That's going to be entirely based on whatever you think is going to be an easier integration in terms of what does your region look like and all that stuff. But this would represent now a volume. Remember, when you started integration, it was to find the area under the curve. Now, we know integration is way beyond just finding areas under curves. In fact, we've used them to find surface areas, arc lengths, volumes, everything. But we can now think of this as literally being volume, where I have the same region in the xy plane that we integrated in Calc 1, but now I have a surface. So I have a three-dimensional shape now. And it can only be done as a double integral because now I have literally an x, a y, and a z in the problem. Okay? Any questions so far? Okay, so I want to go backwards now to remind you again something you know from Calc 1 that will apply here. Now, in Calc 1, every integral that you ever did in Calc 1, let's keep it simple. You were actually calculating the area bounded by curves, okay? Not just area under the curve bounded by the x-axis, but I just had some enclosed region in the xy plane, and we integrated to find it. Every problem that exists, you can integrate with respect to x or with respect to y. There's no rules that say, no, you can only do it with respect to one. No, you chose the easier route. For example, if all your boundaries were given as y as a function of x, then integrating with respect to x is probably way easier. But what if all your boundaries were given as x as a function of y? Then integrating with respect to y would be way easier, because otherwise you'd have to convert, solve, do all this extra work. So every problem can be done both ways, but not all problems are efficient. So let me give you a simple example. This is one I do in Calc 1. This is a Calc 1 problem. Find the area of the region bounded by x equal y squared and y equals about x minus 2. Okay, so looks something like that. So we need to figure out the points of intersection, which is not very hard. Just set the equations equal. So I go back to here, and I'd say, well, let's see. If x equals y squared, then y equals y squared minus 2. So y squared minus y minus 2 is 0. So y minus 2, y plus 1 is 0. So y is 2 or negative 1. Okay, well, if y is 2, then x would be 4. If y is negative 1, then x would be positive 1. Okay, good. I found my 2 points of intersection. So when I do this problem in Calc 1, all the Calc 1 students say, well, we like integrating with respect to x. It's easier to conceptualize. And it's probably true. It doesn't have to be, but so when we do this problem, in Calc 1, we'd say, all right, let's make an arbitrary rectangle. This is the way I show people to do it. Make an arbitrary rectangle and find the area of that rectangle. Then that becomes my integrand if I do it right. You can avoid doing the entire Riemann sum thing if you understand. The progression is you find the area of an arbitrary rectangle, then you set up a sum, then you do the limit, then you write the integral. And we already know what the integral is going to be. It's going to be whatever that looks like. So let's call that the ith area. So it's going to be curve minus line. Oh, I need to solve for y. So y is, I'm going to write it like this. So that's clearly the positive square root, isn't it? So this is going to be the square root of xi minus 2 all times delta xi. Beautiful. And the range of values for x will be what? My x's will range from what to what?
0 to 4.
You sure?
1.
Curve, line, it's only going to be 1 to 4, isn't it? Because from 0 to 1, oh, what's happening between 0 and 1? I have different boundaries, don't I? Oh, and by the way, if we're not mindful of that, we will get something goofy. So I have a second, oh dear. I have a second rectangle. And if you want, we'll call that AJ for just a different one. And that's going to be the positive square root on top and the negative square root on the bottom. So that's going to be root xi minus negative root xi. Those don't cancel, they add. Or actually j. I should say j, because I'm calling it j. And this x is going to range from what?
0 to 1.
0 to 1. Oh. So now I can say my area is the integral from 1 to 4, probably better to use a fractional exponent, x to the 1/2 minus x plus 2 dx plus 0 to 1 of simply 2x to the 1/2 dx. Boy, all right, let's do it. So that's going to be x to the 3/2 times 2/3 minus 1/2 x squared plus 2x from 1 to 4 plus x to the 3/2 times 2/3 times 2. A lot of work, but it's what it is. So if I evaluate it 4 to the 3/2 would be square root cubed, so that'd be 8. So that's going to be 16/3. 16 times negative 1/2 would be minus 8. 8. Now let's evaluate it 1. 2/3 plus 1/2 plus 2. Now on the other side, when I evaluate it 1, it's just going to be 4/3. Okay, now let's add all this up. Either in your head, by your hands, or calculator. But again, always be mindful of this recording, make sure we are actually recording. All right, tell me when you get a value. It's good practice, by the way, if you're Calc 1 integrating anyway. Because all integrations come down to Calc 1 integrals at some point, just like all derivatives come down to Calc 1 derivatives. So what do you guys get? Make it easy.
8.5.
I'm not sure about that. 3.5? Do we have a third one?
Also got 3.5.
So you also got 3.5?
Yeah.
All right. Are my calculations correct? I think my calculations are correct. 1 to 4. 16/3 minus 8 plus 8. Oh, you know what? I just realized. We have a boo-boo here. Yeah, I think that changes our answer. Instead of 3.5, I think it's 4.5 because we just had the wrong way on that one. Or just 9/2. Sorry about that. I couldn't read my own writing. Now, everything we did was true and correct. Was everything we did efficient? Why was this not efficient? It's the ODUB part. Why is it not efficient? I had to find an area by adding two integrals? Who does that? Well, but I want to integrate with respect to x. Well, we forced it, didn't we? What if I had integrated with respect to y? This is the whole point. Every integral that exists, you have this choice. And when I do this problem in Calc 1, believe it or not, most people automatically do what we just did. Yet, what if I did a horizontal rectangle? Then the boundary on the right is always the line, isn't it? And the boundary on the left is always the parabola. So right off the bat, that means I can do this as one integral. But also, my first boundary was x was given as a function of y, so I didn't need to rewrite it. Everything we did was correct. But what we did required two integrations. And that's not efficient in general if I can do it in one. So, what if I had done it the other way? Now or I should say not delta A, sorry. Now my ith area will be this, which will be, oh, now I'm going to need to rewrite the x, aren't I? So x is going to equal y plus 2. So it's going to be the line, which would be yi plus 2 minus the parabola, which would be yi squared. And as we say at my house, yi otta then. And what is the range of values for y? -1 to 2. Good. So is my area simply the integral from -1 to 2 of y plus 2 minus y squared dy? Huh. Well, that looks a lot friendlier for one, no roots. So that would be 1/2 y squared plus 2y minus 1/3 y cubed from -1 to 2. Which would be 2 plus 4 minus 8/3 minus 1/2 minus 2 plus 1/3, and if we add those up, I'm pretty sure they will add up to 9/2. This was much less work, much less challenging. Every problem that exists, you have a choice. You picked the choice that made the route the easiest, if I want to use those words. Okay? Now, before we start actually doing the integration, there's a little bit more Calc 1 setup I want to show you guys, because once you start the process, sometimes you might change your mind. For example, I started that problem and I did two integrals. They go, oh, you know what? Maybe it would have been easier going the other way. You always have this option to change your mind, sometimes even midstream. And that's another thing I'm going to show you. What do you do? The situation is, I have an integration in front of me and I'm not sure if I can do it. What if I change and decide to do it in the other direction? In other words, I was dy dx, I want to do it as dx dy, or something of that nature. Can I ever do that? All right, let's do a similar problem. Find the region bounded by, let's say, y equals the inverse sine x, y equals pi over 2, and x equals 0. All right, well, I know what the sine function looks like. Now the inverse sine, remember, is only defined in this range. So the inverse sine is going to be the inverse of this, so it's just basically going to be the same graph flipped. So the inverse sine is going to look like this. Okay? It doesn't even matter if you know exactly what it looks like, but that's what it's going to look like. So I want the inverse sine, x equals 0 and y equals, okay, so it looks like it's this region right here. All right. No, that's not too bad. I don't have to have a perfect graph, but I do need to know where things are. This is why you graphed in Calc 1. Not because you were ever going to graph, but you had to know what regions look like, because you can't set up boundaries if you don't know what it looks like. So this is what it looks like. This is pretty simple. All right. So my ith area will be pi over 2 minus the inverse sine of xi, delta xi. Oh, I kind of need to know what that value is right there. Well, I know it's this. For the x's, what is that? The inverse sine of what value gives me pi over 2? 1. Because the sine of pi over 2 gives me 1. That's how inverses work. Oh, okay. Inverse sine of 1 gives me pi over 2. Great. So my x's will range from simply 0 to 1. Oh, this is going to be a piece of cake. All right. So my area is the integral from 0 to 1 of pi over 2 minus inverse sine x dx. All right. Oh, that's easy. And the antiderivative of inverse sine of x, of course, is, wait a minute. We know the derivative of inverse sine, don't we? Do we know the antiderivative of inverse sine? Probably not. Oh. Well, I could be clever and use a Calc 2. I could try an integration by parts. I can try all sorts of stuff, but quite frankly, we don't know the antiderivative. We know the derivative. Kind of dead in the water. Or is it that problem again? Yeah, it's that problem. See, we can't integrate inverse sine. We can integrate sine. So why don't we set up the problem so we're integrating sine? Well, how would I do that? I'm showing you the most common thing you're going to have to deal with every time you integrate. In other words, what if I do that instead? Oh, so if y equals inverse sine of x, then what does x equal? Sine of y. And that might make things a lot easier. So if x is the sine of y, then what is this? This is going to be sine of y, x equals sine of y minus x equals 0. From y equals 0 to y equal pi over 2. Oh my gosh. That's pretty simple now, isn't it? Every problem that exists can be done both ways. So now when I get to a three-dimensional problem and I'm trying to figure out how to integrate my region, I can integrate dy dx or dx dy. What does that mean? I can do it as vertical rectangles or I can do it as horizontal rectangles. Every problem that exists can be set up either way. But the integrations themselves might not be trivial in both directions. That, again, always depends on your boundaries. If your boundaries are all given y as a function of x, then ultimately I want to integrate with respect to x. So that's a dy dx situation. If it's x as a function of y, it's the opposite. If it really doesn't matter, you know, because my boundaries are really, really simple, you know, lines and things like that, then it doesn't matter, okay? So, how do you actually do an integration? Because we're gonna do some volume problems in a little bit, but I want to make sure you understand when it comes to setting up. The most common application right now for a double integral is to find volume. Now, let me point this out. I'm going to ask you a quiz. I'm going to ask you to find a volume and calculate a couple double integrals. And some of you will be knuckleheads, and you'll go to the internet, and you'll punch in how to do the problem, and you're going to go to the worst math website that ever existed. I always know because students always seem to find the bad one. You know, you all know there's Evil Math School. Now, you guys, you know, Dr. Evil, where did he go to school? You know, Austin Powers' nemesis? Come on, you guys have all seen Austin Powers. He went to Evil Medical School. That's why he's Dr. Evil. And they actually state that really clearly. There's Evil Math School where people go to get the worst answers I've ever seen. And there's two things that happen every semester in my math classes. It's comical. In Calc 2, my first lecture of the semester, we do center of mass and work. First lecture of Calc 2. So you barely know how to integrate. And about, I don't know, a quarter of the class will come back and give me double and triple integrals to find the center of mass. Now, we don't learn a triple integral for several more weeks, by the way, and we have no use of it yet. We can't even come up with imagine the use of a triple integral for a while. It's way in the future, and there's nothing we're going to do that makes any sense. that would be a triple integral. So I will have Calc 2 students on the first day of class turning in double and triple integral answers to a center of mass. And there isn't any part of it that's correct. And I basically talked to them and said, you need to drop the class now. Because you cheated on the very first easy quiz, of which I already did all the problems and everybody gets 100%, but they cheated on the very first quiz and they went to the internet and didn't have enough sense to know that they don't know what a double or triple integral is on the first day of Calc 2. Now, having said that, the exact same thing happens after this lecture. I will have people turning in answers with triple integrals. You cannot find a volume with a triple integral. It doesn't make any sense whatsoever to do what we're going to do with a triple integral. There is no application, there is no use. But when you go to the terrible website, it will have you do a triple integral on a problem that only has one independent variable. That can't be done, and anything you write isn't going to make any sense whatsoever. So please, don't go to the internet, not only because that's actually cheating, it's plagiarism, it's grounds for expulsion, but it makes you look like a knucklehead that you didn't pay any attention. You can't do anything we're doing with a triple integral. We haven't even defined one yet. and there's only one problem that we're ever going to use a triple integral on, and it's way in the future. Okay, so don't do that. I have to say that every semester, and there will be knuckleheads who they'll give me triple integral answers on the day you learn double integrals. Why? I have no idea why. You can't do a triple integral unless you have 3 independent variables, and we're not going to do anything with 3 independent variables. We're only going to do 2. So double integral is the most we can do. So when I'm evaluating a double integral, okay, let me keep it really simple. Let's say this is x squared y dy dx. Y is going to go, and by the way, don't even try to imagine that there's an application. I just want to get into how do you actually do it, okay? Let's say this is 2 to 4, and this is, or actually, sorry, let me make it easier. Let's say 2x to 4x squared, how's that? And this will go from maybe 1 to 3, I don't know. There's no application, just how do you do an integral? When you guys started integration, you were given integrals, told to integrate them and then evaluate them at the endpoints. The answer can be positive, it could be negative, it could be 0. Don't read anything more into that. Now, if I said, let's set up the integral to find the volume or the surface area or something, now it can't be negative because we're doing an application. We would have to construct it. Agreed? If I said, I want you to find the arc length of a curve, a negative answer is probably not a good answer. Neither would 0. So how do you do this? Well, your first instruction is to integrate with respect to y. So mentally, and by the way, you can also physically do this. Now, here's the other thing I want you to notice. I'm integrating with respect to y. That means these limits, and I'm going to write it in. I don't need you to do this, but many of you will find this useful at first. This is y equals 2x to y equals 4x squared. Because what are these limits? X equals 1 to x equals 3. You're never going to see that in print. You're not going to see the x equal or the y equal. It's implied because of the order of the integration. That's what this means. That's why I'm saying at first, it's probably very wise for you to write it in to make sure you're looking at the right thing, because a lot of times people get it mixed up and they get it backwards. Now, most of our mistakes are going to happen in the next 48 hours. So the first thing I'm going to do is this problem right here. Well, if I had asked you to differentiate this problem, you'd say, I'm only looking at the y. I'm treating x squared as a constant. So if I ask you to integrate this problem, you're only looking at the y. What's the antiderivative of y dy?
1/2 y squared.
1/2 y squared. I'm treating the x as a constant. Everybody cool? But if you wanted to write it as x squared times 1/2 y squared, that'd be okay, just kind of ugly. Now, from 2x to 4x squared, and then still dx. This is my integrand. When all of this is done, this will be purely a function of x. What do I do with those? What do I do with these guys? Where do they go? They go into the y. Okay, very important we realize those guys get plugged into the y. So now I'm going to have 1/2 x squared times 4x squared squared minus 1/2 x squared times 2x quantity squared. I need to simplify the integrand, but now my integrand is purely a function of x, isn't it? At this stage of the problem, you have a single integral. We all know what to do with single integrals, but my single integral needs to have just one variable. Okay? There are single integrals with multiple variables, but not what we're doing. So this single integral really needs to have just one variable. So when I simplify my integrand, that's going to be 16x to the 4th times this, that would be 8x to the 6th. This is going to be 4x squared, so times this will be minus 2x to the 4th. Once I complete the first integration, every problem that we look at should now look like a simple Calc 1 problem because it's going to be a single integral of one variable. Doesn't matter which variable it is, it's always going to be whatever the outer one is. That's always going to be your last integration. You work inside out on these. But this problem now is simple, isn't it? Now get out your calculators. So I have 8/7 x to the 7th minus 2/5 x to the 5th from 1 to 3. All right, so get out that calculator and let's figure out what this is. Tell me when you got an answer. Something over 35. Cheap calculators are the best ones because you have fraction keys. Now, I might have hit a wrong button, but I do know that part.
84,052.
Yeah, I got the same thing. 84,052. It's a rational number. We'll leave it at that. If you need a decimal later, that's fine. That's a rational number. So now, it's the process. It's not the answer. So when you're doing, by the way, could I do the integral of the integral of the integral of the integral? Is there any stoppage? No, I can just keep going on forever, different variables. But the idea is you only integrate one variable at a time, okay? Which one? I start and I work inside out. So I complete this. This has become the integrand. This isn't a separate problem off to the side. This is my integrand. Everything else goes along for the ride. Now, question.
Can you do like a double indefinite integral, or you need to have bounds for x?
Could you do it? Yes, you could. You just will not. We don't really have an application. The question is, can you have an indefinite integral as a double integral? Yes, you could. It gets kind of wonky because of the c's, and right, you'd have multiple plus c's, and so I'd have to have initial conditions, and yeah, that's actually not something we're going to run into. That's probably safer because multiple integration is always for an application. In Calc 1, why did we do indefinite integrals? Because in real life, you're never going to do an indefinite integral. Because you were learning how to integrate. A numerical answer wasn't useful. You learned how to integrate. And then later you said, oh, now let me introduce the definite integral, so now I can actually find a numerical value. So think of it, the integration was to produce the correct function. Now I'm evaluating the function. The definite integral just was the arithmetic step at the very end. It was the antiderivative that was the most important part of the process, but that generally wasn't our final answer. Okay? So it's the integration, is the process is important, but because what we're doing is always going to be finding an area or something. Later, work, different types of applications. I do want a number at the end. Now, in Calc 1, okay, let me do a really simple problem. Calc 1, I have volume. You guys remember doing stuff like this. I have a cube, and it's an inflatable cube, and I'm blowing it up at a certain rate. It's this many cubic centimeters per second, and when it's this, how fast is the length changing? You guys remember doing stuff like that. So volume equals x cubed, and I'll have people do things like this. And I'm a mathematician, and I have no idea what that means. That has no meaning mathematically whatsoever, yet I find calculus students that they love primes. Why does this have no meaning whatsoever? It's not a trick question. You can't do a derivative unless you know what variable you're differentiating with respect to. Because the question you're always asked is this one. Which means it's basically every problem that exists has a chain rule. You always assume everything's a composition of functions. There's a v prime of t and there's a v prime of x in every problem. So what's v prime? I have no idea. Kind of need to tell me what variable you're differentiating with respect to. Oh, does it matter? Probably in every problem that exists, you have more than one potential variable you're in. Oh, so if I don't tell you, then you couldn't possibly know. So here's an issue that we all have. When people say things like this, y prime. Y prime does not equal, in any context, this does not equal dy dx. Y prime has two possible answers. If I'm differentiating with respect to y, it's 1. If I'm differentiating with respect to any other variable, it's 0, because you're saying y is an independent variable, partial derivatives. Okay, this symbol doesn't exist. There is no such thing as a variable prime. There's function prime, but function prime of the independent variable. Nobody writes f prime, they write f prime of x, because there also might be an f prime of t. Oh, in fact, assume there always is. So when it comes to notation, we've got to be careful. So what I would always get on the Calc 1 and 2 students when they're writing integrals, I want you to integrate x squared. What's wrong with this?
No dx.
Yeah, he said, well, why would it matter? Because now you realize that I can put anything there. Everything is fair game. This has perfect meaning. Anybody want to guess what's the answer to this?
0.
Oh, yeah. X squared's a constant. Oh, and so what I emphasize in Calc 1 and 2 is anytime you have an integral, the single most important part of the most important part of your integral is not the integrand. That's the most important part of every integral, is the variable you're integrating with respect to. And I remind people all the time, even in this class, I said, you set up an integral, but you have no variable integration. And they'll say, well, why would that matter? There's only one possibility, isn't there? No, there's actually infinitely many possibilities. And we're going to see on a regular basis. These do not have to match, ever. When they do match, it's a Calc 1 integration. When they don't, it's a Calc 3 integration. And guess what? Most of the time, you're going to have multiple possibilities. So the variable of integration is huge. It tells you what path. Just like when you're differentiating. You need to know the variable you're differentiating with respect to, and then once you do. Now, there's another minor one, and this is not a big deal. You guys' partial derivatives have been off the charts good. So let's keep it simple. I've got the following. This is actually huge. This is why on some of you I'm getting on you about your dx's. Are these the same answer? No. Let's do the second one. It's easier. What's the answer to the second one? 2xy. Well, why are these not the same? What does this notation first tell us? It's an ordinary derivative, but the fact that I'm asking you to do it with respect to x means in that universe, there is only one independent variable, x. All other variables that exist are functions of x. That's how you interpret that. There is no other possible interpretation. This means automatically, because of that notation, that y is now a function of x. So how do I do this one? And I'm pretty sure these aren't even similar answers. Oh, first one's now a product rule because I have a product of functions of x. The second one's a partial derivative. It's easy. That's why it's really important that you make the distinction whether it's an ordinary or partial derivative, because an ordinary derivative means that everything's a function of that one variable. No matter how many variables you put in, they're all functions of the one variable. That's absolute. There's no gray area there. We like that mathematically. There's no possible other interpretation. Wouldn't it be terrible if a question was asked and there were multiple possible interpretations of it that were all correct? That means there's multiple possible correct answers, and we don't like that. I'd like to know that we all are on the same page and we all get the same answer. This is really important that we understand. Now what we're doing, we're writing dx because we're integrating with respect to that one variable. But in a sense, don't write this, but in a sense, these are almost like partials, aren't they? We use the formal dx, dy, dc. We use that in integration, but we treat them more like the partials. Okay, we treat them more in that way because we're not doing chain rules and weird stuff. This integration, I treat dx as a constant in a sense. Now, this is one, this will not help you in the long run, but I want you to understand, okay? If I ask the following question, this is a problem that everybody's in trouble with in Calc 1. This is a Calc 1 problem that people struggle with because you have to do a substitution, but we sometimes forget. So we do weird things. This is Calc 1. So we probably say something like this. Let u equal x minus 2, then my du is 1 dx. Great. So now this is the integral of x times the square root of u du. You like that? Why not? Well, first of all, it's completely unrelated. I won't give the same answer. It's completely wrong for a lot of reasons. Right now, there's only one independent variable. It's x. I'm treating you as a function of x. And there's an absolute in mathematics. And a lot of us get in trouble, and we're going to get in trouble because we forget substitution. You cannot have the dependent and the independent variable in the integral at the same time. That's an absolute impossibility because it produces a completely different answer. These are not equal. This is completely wrong. This is equal to this, by the way. And so when I teach Calc 1 and I ask this question, people will go to the tutoring lab over the years and they'll come back with this answer. Why? Because they went to a Calc 3 tutor who knows how to integrate with multiple variables. They said, oh, just factor it out. Now, if this was the first statement of the problem, then this is actually correct. But this isn't correct to begin with. Why? Because what does x equal?
U plus 2.
U plus 2. So what was the correct thing to do? U plus 2 square root of u du. Now it's an easy integral. Distribute, integrate. Oh, here. But people get in trouble with things like this because the moment you write this, it's impossible. You cannot have the independent and the dependent at the same time because you now have an integral with two variables in it. And an integral with two variables in it is now a Calc 3 integration, like a partial derivative. Oh, so we sometimes get in trouble. I don't want you to ever get in trouble because there's nothing wrong with an integral with two variables. In upper level statistics, it's really common that you're going to do an integration but have more than one variable. And so your answer is not a number, your answer is going to be a function. Okay, we want integrations to produce numbers, but it's actually going to be a function because you're only integrating one of them. And it's necessary to do things like this. In our class, we're doing things that are going to produce numerical answers, so that's really not anything to worry about. So I'm going to do a simple application problem. Okay? Let's find the volume under, I'll keep it simple, f of x, y equals, how about, again, I want to keep this fairly simple. Let's say x squared, y squared. Bounded by, how about, again, I want to keep this really simple. Y equals x, y equals 0, and x equals 4. So I have this surface. The surface is infinite. I'm fluffing the sheets as I'm making the bed, but my sheet is actually infinite. So if I said, what's the volume under my sheet? You'd say, well, it's probably infinite because my sheet's infinite. Oh, no. I mean only the part over the bed. Did I just create a finite block? Yeah. So I have my sheet, but now I'm bounded by the bed frame. In other words, my region in the xy plane would be the shape of the bed. So I have a three-dimensional volume. I gave you a surface, and I gave you the region in the xy plane. The region in the xy plane is what determines your limits of integration. You with me on that? So, first thing I'm going to do is draw the region in the xy plane. So I'm bounded by y equal x, y equals 0, which is, what's y equals 0? Yeah, the x-axis, and x equal 4. So I'm bounded by this triangular region. Is there any advantage to going dx versus dy in terms of my rectangles? Is there any advantage? No, I have linear boundaries. It doesn't make any difference whatsoever. I am more inclined to go with vertical cuts for the simple reason that I'd be bounded by y equal x and y equal 0. I love 0 as a boundary. If I go sideways, I'm bounded by x equal y and x equal constant, which isn't a harder problem, but now I have two things that I have to evaluate. You all realize when 0 is a boundary, and you evaluate, unless you're doing e to the x, evaluating at 0 usually produces 0. So that's why I would tend to go vertical, but horizontal is equally correct. You with me on that? This is my region in the xy plane. Now, the fact that I made a vertical rectangle means I'm going to finish with a dx integration. We're going to set it up both ways, by the way. So, my integrand is independent of the region. The integrand is the roof. Never confuse the region in the xy plane with the roof. When I'm fluffing my sheet, my infinite sheet, my sheet doesn't know the shape of the bed. My sheet doesn't care about the shape of the bed. I'm fluffing my infinite sheet. You're standing on top of the z-axis with a cookie cutter that's in the shape of the bed and you go, what's the shape of our cookie cutter here? Triangle. Does it have anything to do with the surface? No, it's the portion of the surface I'm choosing to use. I could have given you different boundaries, but I still have the same surface, but my cookie cutter would have changed shape. Everybody cool with that? So literally that's what you're talking about. It's a cookie cutter. Here's how we write it in general. This is the question I'm asking you. You are deciding the order. Now, our first time we said, you know what, let's go in this order here, because that seems like a pretty simple setup. Agreed? So now I'll put the things in. I'm going to go dy dx. So y is going to range from y equals 0 to y equal x. Y isn't constant here. I'm going from y equals 0 to y equal x. And I'll write it out. I don't need you to write y equals, but you might need you to write y equals at first. Now, x is going from what to what?
0 to 4.
0 to 4. X is not bounded by functions. X is bounded by constants because x is the outer one. That has to be constant. That has to be constant. So this would be the volume. I'm less interested in the answer right now. I'm more interested in, I want to rewrite this. Question. Question. True or false? Now, we've never done this before, so you don't have anything to rely on, so go with your gut. True or false?
True. False.
Who yells louder? Well, the person who said false, why do you think it's false? This is going to give me a number. What's this going to give me? Function of x. Ooh. What did I say about the outer limits? They have to be constant. So no, they're not the same. Can I just simply switch the integration? No. Yeah. No. That no work. Nope. But we have to see that to believe it. So let's now consider this. Now, x is going from this line to this line. What are my x limits? X is going from x equal y to x equal what? 4. Y is going from y equals 0 to y equal, it's the line y equal x, so it's also 4. because y equal x, that point, probably should have used different, that's the point 4, comma 4. That's why he saw 4 in both directions. But that's not the same, is it? Oh, in fact, this has got a variable down here.